Здравствуйте! Сегодня у нас урок для учащихся 12 класса, которые изучают физику на английском языке. The topic of lesson is the charge particles. It is from Unit 3A for 12th grade. So, why is this of interest? Many people are lucky who have seen our natural phenomena which are called SO, which is very bright dancing lights which you can see above the southern and the northern hemisphere. It's due to the collision of the particles which coming from the sun and enter the atmosphere. We have the different names depend on the place of location. Another thing which also related to our topic is so-called Van Allen belts. You see two belts in and out which consist of positive charge photons and negatively charged electrons. They were opened by Van Allen in 1958. It also was charged and trapped by magnetic field of the Earth. So, but many of us cannot even imagine the charged particles as a base of many devices we are widely used nowadays. We all rely upon the cathode ray tube or CTR. You can see the old-fashioned TV set, nowadays TV, and some scientific devices. So, many people nowadays, some spectrometers, mass spectrometers, cyclotrons, magnetrons, which present the practical technological application of the charged particles. There are 5 learning objectives which we can find in the Unit 3. The first one, show understanding of the main principle of determination of E by Millikan experiment. Summarize and interpret the experimental evidence for quantization of charge. Describe and analyze quantitatively the deflection or beam of the charged particles by uniform electric and uniform magnetic fields. Explain how electric and magnetic field can be used in velocity selection, and explain the main principles of one method for determination of velocity and the charge-mass ratio for electrons. There are some keywords you can introduce as your students, which are very useful for studying this chart. How all this started? In the beginning, we have to mention William Crookes' discovery in 1870s. He has found the very nice glowing of light in the colorful in the sealed glass tube under the low pressure. It was very low pressure. So this
когда вот вылазит ошибка, да? Вы останавливаете, закрываете, потом чтобы не терялось оно, хорошо?
Я закрываю на крестике все, да?
Закрывайте, да, потом вот как с какого слова начали.
Понятно, хорошо. Ну что ж, с этого кадра. William Crookes' discovery was done in 1870s when he has took a very specific glass tube under the low pressure, and so light glow of characteristic color. It happened near the anode, whose force heat was positive, and it was attracted by positive plates, and this glow was easily distorted when magnet was brought near to the tube. What he has found? He understood that the particles, charged particles, move through the gas when it conducts electricity. He called them as cathode rays, and when we took another tube, which nowadays calls Montesa tube, we can see how this ray can even rotate the paddle wheel placed there. But if you place magnet again near the wheel, it cannot be rotated. Let's look our movie. As you see, there is some green color light which is formed in the tube in the nearest side to this cathode. This is anode. So it's bending when we brought magnets. It means it affects the magnets on magnets. So it was found that the cathode ray produced in the discharge tube there were the stream of charged particles which carries a negative charge. You can see this one on this diagram, and you can watch same movie on YouTube channel. So we have to recall some very important things for us to go further in our consideration. These are two moments: motion of the charge in the electric field, motion of the charge in the magnetic field. The charged particles in electric field experience a force which is equal to the product of the wave, field length, strength, and the charge. But this formula phi F is equal to QE. But if you look at this diagram, you can see how the trajectory of charge depends on the charge on the plates and the charge of the particle itself. If charge move along the lines of electrical field, we do not change the direction. But if enter the region between the of electrical field, they deflect to the plates depending on the charge. Look here, positive moves toward to the negative charge plates, and the negative charge moves inverse. So with the property of the action of a uniform flow field on the charge placed in electrical field are known nowadays as electrostatic deflection. Its action effect is similar to the action of gravity, which makes all the object in its field change its direction toward the center of the Earth. So, an electric field can be used to deflect beam of charged particles when the very important condition when the field is applied to the right angle to the path of the beam. So there is some simulation in the internet which let you to train yourself and observe the real deflection of the particles in the electric field. You can manipulate by velocity, you can manipulate by the charge of the plates, and if you launch, you can measure time and observe the motion of the charged particles, how they deflect in the electric field. But for us it's very important to know how do really we can see the deflection of the beam or even the motion of the charged particles in the electrical field. So-called cathode ray tube or CTR in brief show you the real motion of the particles when we see some image on the screen. I'll just again put here a diagram which shows you the deflection of the beam. You can measure all distances and even can evaluate some charge if you use with CTR in the oscilloscope, or just you can find your image by watching TV. Let's now see some simple movies which shows how cathode ray tube works, the base, a simple basic unit of it, and how the electric field and magnetic field affect to the motion of the charged particles. Let's watch.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes this specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction.
You can see some the structure of electricity tubes. You see the cathode, anode, power deflect. You may observe how we apply electric field is applied, how magnetic field is applied. Okay, so action with the ability of the charged particles react on the action of magnetic field. Actually, as you can be seen on this movie, when negative charge DN fragments migrate through the gel in response to the applied magnetic field with so-called gel electrophoresis. Now let's briefly consider the motion of charge in uniform magnetic field. You can watch a very simple one of the movie when you should be very attentive to observe how charged particles change direction depending on the angle of entering, of the way entering, dependent on the direction of the magnetic field. So let's see this movie. We have summarized the things we have seen in the movie related to the charged particles. The main things which happens with charged particles which enter the magnetic field region under the right angle is invert with its changed its direction and moves in the circular trajectory. It happens because of the direction of the field is perpendicular to the direction of the velocity. Here we have used crossed, it means the field is directed toward the screen plates. Then with a magnetic field now which at right angle to the velocity from correspond to the centripetal force, which is the reason why the particles now change trajectory and start to rotate in the magnetic field. Whereas some formulas which let us to evaluate, for example, to find the radius of the circular path. You see the formula which is a Lorentz force formula we called, which let us to find the force of a magnetic field dependent on the velocity, charge, magnetic field intensity. And if you combine two formulas together, I mean centripetal force and magnetic field, balancing them, we can actually get expression to calculate R. But interesting things happens when, in this case, the motion will be the spiral or helical. It means because magnetic field can act only on the perpendicular component of the velocity and does not affect on the horizontal component, which may let the particles move straight. So, with cathode rays has proved that they were really negatively charged, and nowadays they are known as electron. You see on the picture Joseph J. Thomson, which studied, who made his investigation in laboratory in his laboratory. So, in his idea was in that he combines the action of electric and magnetic field. So he designed special tubes, you see, consisted of cathode, which emits electrodes, and which electrode to palm beams move to the direction of anodes charged positively. And then with the cathode rays produced, which now passing through the two parallel plates, which provide the existence of electrical field, and two outer coils have been used to form magnetic field, and the magnetic cathode rays which pass through the region of electric and magnetic field when deflect or can strike the screen and cause some glowing, which led to find the deflection of the beam and calculate, for example, the radius of the trajectory. So he can manipulate the voltage on the screen, the electric field intensity by changing voltage, and he can manipulate and change the magnetic field strength by changing of current at the coils. Simple experiment was evaluating electric and magnetic field and evaluating magnetic and centripetal force. If you balance two forces and this balanced force act on the beam, we can work out so-called specific charge of electrons. Let's watch some movies. This is interesting experiment which internet resource which let you understand the idea of Thomson, results he has got in the end, and the value of so-called specific charge ratio, charge or charge mass ratio.
Molecules. In 1897, J.J. Thomson performed the first experimental measurement of the charge-to-mass ratio of an electron. Thomson used a cathode ray tube, a device that generates a stream of electrons. Here is the setup used in the experiment. In order to minimize collisions between the electron beam and the molecules in the air, Thomson removed virtually all of the air from within the glass tube. Inside the cathode ray tube, an electric field is produced by a large potential difference between the cathode and the anode. Electrons are emitted from the cathode and are accelerated toward the anodes by the electric field. Some of the electrons pass through the slits in the anodes, forming a narrow beam. When the electrons reach the end of the tube, they strike a fluorescent coating, causing it to glow. Thomson used electric and magnetic fields to exert force on and deflect the electron beam as it passed through the tube. The electric field, which was produced by charged parallel plates, was oriented perpendicular to the beam. The electric field, of strength E, produced a force equal to QE that acted on the electrons and deflected them upward toward the positive plate. The magnetic field was produced by two electromagnets and was oriented at right angles to both the beam and the electric field. Recall that the force exerted by a magnetic field is perpendicular to the field and to the direction of motion of the electrons. Thus, the magnetic field of strength B produced a force equal to BQV, where V is the electron velocity, that acted on the electrons and deflected them downward. The electric and magnetic fields could be adjusted until a beam of electrons followed a straight or undeflected path. When this occurred, the forces due to the two fields were equal in magnitude and opposite in direction. Mathematically, this can be represented as shown here. Solving this equation for V yields the following expression. This equation shows that the forces are balanced, only for electrons that have a specific velocity, v. If the electric field is turned off, only the force due to the magnetic field remains. The magnetic force is perpendicular to the direction of motion of the electrons, causing them to undergo centripetal, center-directed, acceleration. The accelerating electrons follow a circular path of radius r. Using Newton's second law of motion, the following equation can be written to describe the electron's path. Solving for q divided by m results in the equation shown here. Thomson calculated the straight trajectory velocity, v, using measured values of e and b. Next, he measured the distance between the spot formed by the undeflected beam and the spot formed when the magnetic field acted on the beam. Using this distance, he calculated the radius of the electron's circular path, r. Knowing the value of r, Thomson was able to calculate q divided by m. By averaging many experimental trials, he determined that q divided by m equal to 1.759 multiplied by 10 to the power 11c divided by kg. Using this value for q divided by m and the known value of q, the mass of the electron, m, was calculated.
For better understanding this experiment, you also may use simulation, which also available in internet, which called Thomson experiment. You can study the structure of the tube used by Thomson. You can also try to change voltage, to change magnetic field, to change electric field. If you now follow the step of Thomson and balance two forces, electric and magnetic ones, you can find the ratio of charge and mass. Experiments show that if you have only electrical field, the charge deflected, for example, on how it is on the screen, downwards. But if you switch electric field and switch off electric field and switch on only magnetic field, the beam start deflected in opposite direction. So if you now can switch totally electric field and use only magnetic field, we can easily calculate the radius of deflection of this field. And now using this arc, you see this arc which we see on the screen, calculate the radius, and radius can be used to find the ratio of charge and mass. In his experiment, Thomson got the next value. Mass of electron to charge of electron to mass has been found in terms of voltage applied to the deflected plates and the value of magnetic field which was produced by magnetic coils. And I have said we can calculate R by using special scale on the screen of the tube, and the value have got by Thomson was 1.75 multiplied by 10 in 11th degree coulomb per kilogram. We can notice that at the time of Thomson there were no scales on the screen, and he used simple ruler to calculate the deflection of ray. But nowadays devices let us to measure angle of deflection, and it simplifies our work. Why we have to study Thomson experiment? In what its significance? Thomson's work really the story of discovery electron and represents the birth of subaltern particle physics. He also won Nobel Prize for development of electron, for opening of electrons and model of atoms, like Crook, which won Nobel Prize for discovering the cathode ray tubes. But Thomson's works was the started of subatomic particle physics, and his result was developed by Millikan, which established the charge on electrons, which now is elementary charge. But many scientists thought that discovery of Thomson has made more impact on physics, on science, on technology, in our daily lives. We now can look at some application how the charged particle is used by the people. So I have mentioned today about cathode ray tubes is a part of the electronic device which let us study electrical oscillation or any oscillation which turn to the electrical one. So it consists of simple so-called electric gun which is responsible to fire electrodes which pass through the anodes which make to follow one direction, and two plates of horizontal and vertical deflection plates. Finally, we can see this glow of electron due to the striking of this of material covered by screen. On the screen, it means the image produced. But interesting things when we can use the idea of Thomson is so-called velocity selection. Very often is so important to select charged particles which have a certain velocity, and the chamber is constructed this way using by idea of Thomson that only particles which have a certain velocity can enter to the deflection chamber. With combination of the slits and deflection chamber is present a velocity selector. You see, source of electrons or any particles can pass in the region those electrical field which are between two plates. But at the same time we have magnetic field. In this case, when the positive charge particles will deflect to the negative charge particle. But if you now switch on magnetic field, it changes the initial direction of the charged particles and makes in the case when the value of magnetic field will be equal to the value of magnetic force, the force from magnetic field, look here the condition mathematically, we can see the velocity will be defined by a ratio of intensity of electric and magnetic field. So only will the charge particles, which velocity to correspond to this value for definite magnitude of the field and definite magnitude of magnetic field. Electric and magnetic field can enter this chamber. You see the condition, electrostatic force and magnetic field. It is the base of work any velocity selector. Another application which widely used mostly in not only physics and chemistry, it is a so-called mass spectrometer. It was developed by 1919 by Astana, and nowadays it is an instrument for measuring mass of isotopes. This is a structure to find the mass of the mass of these isotopes by using the knowledge of application of electric and magnetic field. But we go further and let's move to the Millikan experiment, which is also famous, and it's called oil drop experiment. The idea was in that he wanted to find the charge of electrons, and therefore he used the idea charge particle plates, gravitational electric force, and the total force. Let's watch some simple movie of this experiment.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
The idea was in which the particles, the oils will spray through the atomizer, and like perfume spray, due to the collision we get some charge. And when they pass through the hole, they started to move down due to the gravity force, but the viscosity force, which also makes some resistance. But if you now charge the plates and control the electric field between them, we can even to make it to the particles stay stationary between two plates. So the physics of this idea was in that you see the mathematical expression, and the charged particles can be depend on the mass of the drop and the size of this drop, because also and distance between the plates. When drop is suspended, forces due to gravity equals to the force of electrical fields. The main idea of the experiment done by Millikan was in that he has found the charge of simple electrons. You know, you use nowadays value and mass of electron. But if you look at the original data, which printed in 1911, you see he did not publish all the data. He used only data which, from his point of view, have good satisfaction and can be integral to some numbers. For example, he rounded the whole number 12, 6, 17, and he has found that the all charge are more integral part of the elementary charge. This is now is known as a quantization. It's known as a that any elementary charge cannot be any charge can be broken down only to the elementary charge, which are called electrons. So let's consider what does mean the charge is quantized. Quantization is a concept that physical quantity have only certain discrete value. We can use, for example, analogy. If you now would like to build a wall, you can use a brick. But each brick, if you use one brick, use two bricks, another 10, 11, but all of the whole wall will consist of the simple unit which is brick. Therefore, any charge also is a composition of so-called elementary particles, and therefore electric charge is integral multiple of the smallest possible elementary charge. Millikan states that this result to be direct and tangible demonstration of the correctness of the view that all electrical charge, however produced, are exact multiples of one definite elementary electrical charge. And he thought and he recognized, and nowadays we confirm that there are two in physical quantity which very important nowadays. It's velocity of lights and the elementary electrical charge. So while we cover material of this unit, to achieve the goals which we announced at the beginning of the lessons, you can look at these success criteria. What skills do you have? Must you exhibit? What application skills you can show us? How analytical and research skills can be demonstrated by the students while it when he would be assessed on this topic. Students know the action of electrical magnetic fields in the charge, understand what is mean quantization, able to describe structure and work of CTR, able to describe Thomson and Millikan experiment, because we have to explain one method to determination charge and the mass of ratio charge and mass, and the very important skills each able to solve the problems when can use any conclusion coming from the experimental methods used in study of charged particles. I also wish to summarize or just to put all knowledge in order. Just be confident that you know exactly, to make some concept map or mind map when the main like this one or another one. So place main ideas, charged particles, what steps of discovery or investigation you can mention, what main experiment have been done by teacher, what the main conclusions follows from this experiment. So it's very important to reflect on any things you have learned or studying or learning. So we use the scheme of the next. So the first is so double free. What works well while you study or just observe this lesson? So what, according to your opinion, was good or request to work out? So the second reflection point is MRE. My response is preparing the material for this lesson. The course plan on physics of the last issues was being used. So the material was based on the physics course, Cambridge International AC and A level, and advancing physics for understanding physics for advanced level, and some sites. These sites, the link to these sites are for simulation, which is very useful for this unit, because we are not able to provide experimental evidence of theory studied, but virtual help us to understand the core of experiment and simplify our understanding the charged particle structure and physics of the charged particles. Thank you for your attention. All materials can be found at the Moodle site.